Hi everybody, this is Nifish. In today's lecture, we're going to go over LFM chirping. So basically, LFM is linear frequency modulated chirp, and this is one of the techniques we use in automotive radars. Okay, so basically, we are going to generate a chirp, and then we are going to draw the frequency and time graph. And from that plot, we can learn a lot, like how can we get the range resolution, max range, max velocity, velocity resolution, and how they are interdependent. So basically, these are the main three things we're going to go over. And as a reference material, I would say like you can go over Texas Instruments Fundamentals of Wave Radar Sensors. It's available online for all of us. Okay, so I have imported NumPy as NP and Matplotlib as PLT, and I will start just drawing a sinusoidal wave. Okay, so let's say our signal is A is the amplitude, and then we have NP dot cos, then 2 times NP dot pi times f times t. So this is a equation, sinusoidal wave equation. I think all of us are familiar. Okay, and let's define the frequency. So let's say 10 hertz, and then we have a time. Let's say start is 0 and t stop is 1 second. Okay, so we are going to generate a signal that's going to start at 0 and stop at 1. Okay, and the total duration of the signal is np dot linear space, and then we have the t start, right? So start and then t stop, and then we need to define how many number of samples we want to have. So let's say 1000, and basically n is going to be here. So at the beginning, I'm just trying to plot a sinusoidal wave, and from there we'll get to know how can we generate a chirp. Okay, so let's plot this out. So plot um, time, we have x-axis, and then we have the signal. Okay, so let's run all of it, and let's visualize the signal. A is not defined. Let's say for simplicity, amplitude is 1. Okay, so let's run again. And okay, so this is a sinusoidal wave, and you see there is no change in the frequency. Frequency is constant here, right? But in the LFM, linear frequency modulation, we are going to change the frequency, and I'm just going to show you how. So since we're going to change the frequency, this term I'm just commenting out, and let's say we have a start frequency. Okay, so if a start is, let's say, 1 hertz, and if stop is 10 hertz. Okay, so basically these are the two inputs to frequency synthesizer. Okay, and that synth is going to give you an output, which is there's an equation for that, but basically this is a 3-port device. These two are the inputs and this is the output. Okay, and the output I can just write it down. F start, so we have the start frequency and then the bandwidth. Okay, so the bandwidth is going to be F stop minus F start, right? So this is going to be the bandwidth, right? And then I'm just going to put it in a rounded bracket, this thing, and this thing is going to be multiplied by the slope, which is, we have the time, right? So this is the total duration, right? And how the signal is changing over time. That means we need to have these t stop. Okay, so this is kind of you can say like this is the slope right here. Okay, changing of the signal, and this is the bandwidth. Okay, and this is the start frequency. So you see, like from the inputs, the f start and f stop, we can derive the output. Okay, and since we are going to use the instantaneous, just going need to divide it by 2. Okay, so we have the f output, right? So instead of using this f here in the sinusoidal signal we had at the beginning, we are just going to replace it with f out. Okay, which is, it's not showing up here because I didn't run it. So f out, let's run this whole thing again. So we have this, and then the start and stop, and then okay, so this is the chirp. So you see now we are changing the signal over time, because you can see like the cycles, the frequency here it is a low frequency, but the cycles are getting increased, right, over the time. So meaning we are changing the frequency. So now this is not a single frequency. You are starting at 1 and then you are kind of ramping up to 10. So basically you are increasing the frequency. So this is called a linear frequency modulation, LFM, and this is one of the waveforms we use in automotive radars. Okay, and another thing we should draw, that is called FT plot. You see here, frequency and time plot. Okay, so what we can do, PLT dot plot, and then we have the time and we have the fake output, right here. Okay, but we have to do one thing. This is compensated for instantaneous phase, so just need to make one change here. This term is going to be, there will be no division here, okay, by 2. So now let's plot it out. Okay, so you see, this is in the y-axis, we have frequency. Let me write it down. Okay, so we have in x-axis we have the time, right? And then in y-axis, plt dot y label, we have the frequency, right? Okay, so let's run it again. Okay, so you see, like, we are starting at 1 and we are going up to 10. Okay, and within the time duration, 1 second. So this is time and this is frequency. But you can also say the bandwidth here is 10, the stop frequency minus the start frequency, right? And also we have the time, the chip duration is 0 to 1. Okay, so this is what's going on here. Okay, so you can derive two parameters, which is very important for the radar. I will just show like some of the equations how they are dependent, but bandwidth and chip time, you can just see how you can get it from this ft plot. Okay, so this plot can also, we can have negative ramp, or like, like you see, we are starting at 1 hertz and we're going to 10, right? Rather than doing this, we can start at 10 and we can stop at 1. Okay, and let's run it out. So you see, when we are starting at 10, we are having higher frequency, but uh, as we go further in time, we are just reducing the frequency component, right? Okay, and in this ft plot, in this case, you see, we are having the same bandwidth. Okay, but we are just doing a ramp that is starting from a higher frequency and going to the low frequency. Okay, now for the usually, like for automotive radar, I'm just not going to change these parameters here, but this thing right here is 7, because we have a defined frequency um, limit, right? Like we can have a bandwidth from 76 to 81, but let's say usually like we do ramping from 76 to 77, or the reverse, like 77 to 76, 78, whatever you want, like whatever is the design parameter. But this thing is going to be changed for that case. And also the time duration here, you see the chip time here is 1 second, right? We're starting at 0 and is stopping at 1. Usually in that case, it's in microseconds, like 40, 20, 40 um, microseconds. Okay, microseconds. Okay, so this is kind of like, but since for simplicity, just going to keep it, the parameters as it is. Okay, and we are going to do a couple of things here. So we see the bandwidth here, right? Now, this we have two more parameters. Okay, one is the range resolution. Range resolution. Okay, this is the radar's ability to distinguish two objects. They are very closely spaced. Okay, and this term, this is dependent on the bandwidth. Okay, so you have c over 2 times the bandwidth. Okay, so basically, the more you have the bandwidth, the more resolution you have in the radar, meaning the more closely spaced object you can figure out. Okay, so in this case, you see, we have the bandwidth here 10, but if we have a bandwidth 5, then the resolution will be decreased. Okay, so this is one thing. Then we have the maximum range. Okay, one thing is the max range, and this is the story here is this is dependent on the slope. So how um, the max range, this is going to be the sampling frequency, fs, times time, sorry, yeah, the time for the light to flight, and then we have I think it's 2 times the slope. Okay, so the max range and the range resolution, you can see, like if you have more bandwidth, we are going to get better resolution. But the bandwidth here basically is the equation is tc, which is the time right here, um, times by the slope. Okay, so slope time. Okay, and if we decrease the slope time, meaning the bandwidth will be decreased. Okay, so basically these two equations, if you want to have more bandwidth, you are going to have, you need to compromise the maximum range, because they are kind of, the slope is inversely proportional, right? So I want to draw one more plot right here, just to show you, like, if example. Okay, here I'm just going to reduce this bandwidth by half. Okay, so if out divided by 2. Okay, and then I'm just going to plot it out again. So plt dot plot, and then we have this t and f example right here, color with red. Okay, and then plot it out. Okay, so you can see here, this is like the slope here. This is lower than this guy, right? Because you see, if since this slope is lower, like it's taking the same time, but the change of rate of the frequency is lower than this guy, right? So the bandwidth is, that's why the bandwidth is also low. Okay, because this is proportional, and you just need to relate, like, how they are dependent here. So one term, if you want to increase one term, you have to compromise the other term. Same with the um, Doppler, okay, or the velocity. Let me write velocity, resolution, okay, and this term is going to be, um, I think it's lambda, so the frequency, and that's going to be divided by 2 times TF, okay. So TF is not nothing but um, it's like total chips you are going to have, okay, and multiplied by tc, okay. So basically here you have only one chip, right? So the more number of chips you have, the more resolution you are going to get, and the max velocity you are going to achieve is same thing, lambda, and that's going to be 2, uh, I think it's 4 times TC. Okay. So basically the cheat time. So the more cheat time you have, the more velocity you can pick up. Okay. So the car traveling like at 70, 80 miles per hour, you can just see like what is the max velocity your radar is going to pick up, what is the resolution, and we have to drive these parameters. And basically we need to come up with some bandwidth number and with some chip time. Okay. So these are the parameters, like these are the main couple of parameters you have to derive from the requirements, okay, from here. So basically in our next lesson we are going to go deep in these sections, but here we're just generating some chip, like showing how to generate the chips, how to draw the ft curve, and like how the bandwidth matters, how the chip time is going to relate with this velocity, resolution, max velocity, range and resolution, everything. So basically these two parameters right here is going to derive all this.